Let's get some more practice with polar coordinates and integrals with an example which is pretty similar to the previous one. We're given an iterated integral in Euclidean coordinates and we're asked to evaluate it. Now, like in the previous example, there's no indication in the statement of the problem that polar coordinates is the thing to do, but there are a couple implicit indications that this is a good idea. One of these is the presence of x squared plus y squared in the integrand. Another indication is this upper bound here. This is an x bound, which means the relevant boundary equation is x equals the square root of 9 minus y squared. And if I simplify this a little bit, this turns into a familiar looking circle equation. So I have x squared plus y squared, and I also have a circular region as part of my domain. So these are indications that polar coordinates might be a good idea. As usual, I'll begin by thinking about the picture of this region, and I'll do that by unraveling these boundary conditions that we're given. The inside integral with respect to x tells me that x ranges from 3/2 up to the square root of 9 minus y squared. And the outer bounds give me constraints on y. Y has to be between negative 3 root 3 over 2 and positive 3 root 3 over 2. Let's see if we can sketch a picture of this region in the xy plane. How do I do that? I take each of these inequalities and I turn them into equalities. From this first line I'll get two, one of them being x equals 3/2 and one of them being x equals square root of 9 minus y squared, which up here we simplified a little bit already into the circle equation, x squared plus y squared equals 9. So there's our circle. Circle has radius 3 according to this equation. And then x equals 3/2, this is going to be a vertical line sitting over the point 3/2, which is 1.5, which means it's probably right here. Likewise, these two inequalities for y give us two equations. Y equals plus and minus 3 root 3 over 2. As in the previous example, I'm guessing that those coincide with these corners here. We can verify this mathematically by just checking that the point 3/2, comma, blah, 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 lies on this circle. Let me do that over here on the side. If we compute 3/2 squared plus one of these y values squared, what do we get? Well, we'll get 9 over 4 plus 9 times 3 is 27 over 4, which is 36 over 4, which is 9. So that checks out, and what that tells us is that these horizontal lines, y equals plus and minus blah, 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 they run right through these corners of intersections with this vertical line and the circle. All of this is to say that in the xy plane, the region that we're integrating over is this lemon slice right here. Ultimately, what we want to do is we want to describe this same region in the r theta plane. Let's think about r first, and I'll think about it on the picture over here. Geometrically, how do we determine r? Well, typically if we set up a polar integral with theta on the outside and r on the inside, we're fixing a value of theta and letting r vary. This amounts to drawing rays emanating from the origin. So if I fix a value of theta and let r vary, I get slices like this. Fix an angle, let r vary, and I get a slice like this, etc. The lower bound for each of these rays is determined by this vertical line. When I start walking from the origin, the first thing I hit is the vertical red line, and the outer bound is determined by the circle. So with my picture over here, I've visually identified that the lower bound is cut out by this vertical line. Well, that vertical line has equation x equals 3/2. So to get the bound for r, I can just convert this data into polar coordinates and solve for r. X is r cosine theta. So solving for r tells us that the lower bound for r, it looks like is going to be 3 over 2 cosine theta, which is a little funny looking, but that's okay. Now the upper bound for r is given by the circle equation, which is here in red. X squared plus y squared equals 9. If I do the same thing and convert this into polar data, x squared plus y squared is r squared. 9 is still 9 in polar coordinates. and then solve for r by taking a square root, and we get r equals 3. So once we set up the integral in terms of r and theta, we've got our r bounds right here. So just so we have a visual reference in the r theta world, here's what these two curves look like. In the r theta world, I've got r equals 3, which is a horizontal line. And then this one's a little hard to visualize, but 3 over 2 cosine theta is going to look like this. If you don't believe me, you could graph this in Wolfram Alpha or something. But hopefully it makes sense geometrically what's happening over here. At an angle of 0, the radius that we start at is 3/2, which means that here this height is 3/2. It's like 1.5. And then as theta increases, eventually r reaches 3 at its maximum, at least on the region that we care about. So as theta increases, r reaches 3. Likewise, as theta decreases, it also eventually reaches 3. So what we're finding is that the region in the r theta world that we care about looks like this. So one way to think about what we're doing with this polar coordinate description is we're doing a change of coordinates in the original iterated integral by starting with a map over here in the r theta world over this region, and I map that lemon region onto this lemon region. Finally, we need the bounds for theta, which on my picture over here I can see corresponds to whatever this value is and whatever this value is. Geometrically, on the picture in the xy world, the upper bound corresponds to this angle, and the lower bound corresponds to that angle. So what we need to do is figure out exactly what those angles are. There's a number of ways that we can think about this, but what I would do is I would identify that these relevant angles that we care about are going to be dictated by the intersection of this blue horizontal line and the red vertical line. The red vertical line was x equals 3/2, and the blue horizontal lines were y equals plus and minus 3√3 over 2. Now recall that when we talk about standard polar coordinates, we can relate theta to x and y via the tangent function. We know that tangent of theta is y over x. So at these points of interest, which dictate the bounds for theta that we have, tangent of theta is going to be, well, what is y over x? 3√3 over 2 divided by 3 over 2 is just √3. Likewise, with the negative sign, we'd get negative √3. So tangent of the relevant angles that we care about are plus and minus √3. And then if you remember standard values of tangent, you can probably identify the relevant angles. But one kind of tricky way to think about this is that √3 is like √3 over 2 over 1 over 2. And then here it's easier to see what sine and cosine need to be. Sine should be √3 over 2, and cosine should be 1/2, which means that theta is going to be plus or minus pi over 3, probably. And here we have the theta bounds. So this, in the theta r world, would correspond to the vertical line theta equals pi over 3, and this would be theta equals negative pi over 3. Okay, and with all that hard work out of the way, we're finally ready to convert the original iterated integral up here into a polar one. So let's do that. So here's the original iterated integral we started with. When we convert this to polar, we need to change the differentials. Well, with polar coordinates, that's standard, right? We pick up an extra copy of r. So the dx dy is going to turn into r dr d theta. We need to change the integrand. X in polar coordinates is r cosine theta, so here we'll get an r cosine theta in the numerator. And then in the denominator, we've got x squared plus y squared. That was one of the tip-offs that we were going to use polar coordinates. That turns into r squared. Now I'm integrating with respect to r first, and we've got our r bounds up here in purple. The lower bound was 3 over 2 cosine theta, and the upper bound is 3. And then in maroon, or whatever this color is, are our theta bounds. Negative pi over 3 to pi over 3. And now we're in business. This is just a matter of evaluating this iterated integral, and we'll be done. So let's see if I can do this without messing up. Here I've got r squared over r squared. They all cancel out, so the integrand is just cosine theta. When I integrate cosine theta with respect to r, Cosine theta is constant, so I just get r cosine theta. And then I evaluate this at my upper and lower bound and subtract. That'll leave me with 3 cosine theta minus, when you set r equal to 3 over 2 cosine theta, the cosine thetas cancel out, which is kind of nice, and we get 3 over 2. Then we take this home. The antiderivative here is going to be 3 sine of theta minus 3 over 2 theta. Pop in plus and minus pi over 3. Sine of pi over 3 is root 3 over 2. So I'll get 3 times root 3 over 2 minus 3 over 2 times pi over 3. That should be pi over 2. Minus, then I plug in negative pi over 3. Sine of negative pi over 3 is negative root 3 over 2. Minus 3 over 2 times negative pi over 3. I could turn that into a plus here, and then I get pi over 2. And then if I can simplify this in my head correctly, this is like this plus this, which is 3 root 3. And the negative pi over 2 minus pi over 2 is minus pi. And up to possible computational mistakes, we are done. Here's one more example of thinking about double integrals in terms of polar coordinates. This one's a little odd, but it's fun. So I have a region E. It's contained between two lines, y equals root 3x and y equals 1 over root 3x. And it's also a region contained by some circle. What we want to do is we want to set up an iterated integral that gives the area of this region. Now, as with all of these examples, nowhere in the statement of the problem have I said anything about polar coordinates. But one indication that polar coordinates might be a good idea is the fact that this region lives inside some kind of circle. But this is just a thought at this point, and I don't know, we'll see. As always, we can start this off by sketching a picture of this region that we care about, and then from there we can identify how we want to set the integral up. One of the pieces here is a circle. Now, if I look at this circle equation carefully, the center of the circle is at the point 1, 1, and the radius is 1. That means that when I draw this circle, it's going to skim the point 0, 1 here. It's going to skim the point 1, 0, and it'll look like that. Thank God for the Notability autocorrect. The other component of this region is these two lines. These are both lines passing through the origin. In other words, they're rays, right? One of them has a slope of root 3. I don't know exactly what that looks like here, but it's sort of not so important for the sake of the picture. Let's just say it looks like this. And then the other one has a slope 1 over root 3. That's a smaller slope, so again, it doesn't really matter exactly what it looks like, but it's a ray with smaller slopes, so it's going to look something like this. And so the region contained between these lines and in the circle visually is right here. All we need to do is set up an iterated integral expression that gives the area of this region. Now, as a double integral, this is old news. We know that the area is just given by the double integral over the region E of 1 dA. The goal of the problem is to convert this into an iterated integral. Now, as I said at the beginning of this example, I didn't say anything about polar coordinates. We don't have to use polar coordinates. If you want to, you could set this up as an iterated integral expression in terms of x and y. The problem here is that it'd be pretty awkward. This region is definitely not simple in any horizontal or vertical sense. You could split it up into simple regions, but here's what you'd have to do. We'd have to have a split here corresponding to this kink. We'd also have to have a split here corresponding to this kink, and corresponding to this one, we'd have to have a horizontal split. And depending on how the slopes of the lines actually match up, we're looking at like 1, 2, 3, 4, 5, 6, 5 or 6 different regions, depending on how things shake out. You could do it, but I don't want to have to set up 6 different iterated integrals. So instead of doing that, we can probably do this in one swoop with polar coordinates. Indeed, this is a radial region. It's a radially simple region in the sense that if I fix an angle theta and I start walking, eventually I hit this part of the circle, that dictates my lower bound for r, and then I walk, 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 and then I eventually hit the other part of the circle, which dictates the upper bound. And for any theta in the region that I care about, the rays will look exactly like that. There's a consistent lower bound given by this part of the circle, and there's a consistent upper bound given by this part of the circle. So because this is a radially simple region, polar coordinates seem like the way to go. So ultimately what we want to do is we want to set this up as an iterated integral. 1 stays 1, and then dA, when we talk about this in the polar world, as we've been doing, we pick up an extra copy of r dr d theta. Tough part is just figuring out these bounds. In this example, the theta bounds, geometrically at least, look relatively clear. They're dictated exactly by these blue lines, right? The angles of the rays I care about start here, and they swoop out and end here. So the lower bound of theta is going to be algebraically dictated by this condition, and likewise the upper bound with this condition. So this is old news at this point. We can take this data, turn it into polar coordinates, and get the bounds for theta that way. In particular, this lower equation, if I divide by x, this turns into y over x equals 1 over root 3. And then I remember, oh yeah, y over x, that's tangent of theta. So this says tangent of theta is 1 over root 3. And then similar to the trick that I talked about in the previous example, I could cleverly think about this as being 1/2 over root 3 over 2, sine over cosine. And it's easier for me to see now that theta should probably be pi over 6. So there's our theta bound, and likewise we can get the upper bound with this guy. The other blue equation tells us that y over x is root 3. So tangent of theta is root 3, and then again, like we saw in the previous example, that means that theta is pi over 3. So 2 bounds down, 2 to go. This is where things get a little interesting. Visually, the lower bound and the upper bound for r are dictated by the red circle. Different parts of the red circle, but the red circle nonetheless. This is a phenomenon that we haven't seen in the previous examples. What that means is that algebraically, this red circle, it should give us both bounds. So the upper and lower bounds are dictated by this circle equation. That might seem a little funny, and it is, but this is a good principle of stuff that I've talked about in previous examples, which is once you use your picture to identify the relevant bounds visually, at that point you can just trust the algebra. Take the relevant algebraic data, convert it into polar coordinates, solve for the variable that you care about, and things should work out. It may seem mysterious how that will happen, but let's try. Geometrically, we've identified that the lower and upper bounds come from this equation, so we should be able to just convert this into polar coordinates and get the bounds that way. Now, as usual, I'll probably multiply some stuff out here to simplify things. This says x squared minus 2x plus 1 plus y squared minus 2y plus 1 equals 1. And I can cancel out one of the 1's, and I get x squared minus 2x plus y squared minus 2y plus 1 equals 0. And from there, there's not a whole lot that we can drastically simplify. So let's just take this whole thing, pop it into polar coordinates. Now here, I've got an x squared plus y squared. That's going to turn into an r squared. And then minus 2x is minus 2r cosine theta. Minus 2y is minus 2r sine theta. Plus 1 equals 0. And aside from factoring out a negative 2r from these two terms here, there's not a whole lot more simplification that we can do. And it looks a little intimidating, but, and this is kind of the magic of this problem, this is a quadratic equation in R. So it seems a little weird, but we can use, for example, the quadratic formula to solve for R. And when we have a quadratic equation like this in R, we could get two different solutions. That's exactly what's happening here. From this one equation, we get two different solutions. Those two different solutions are going to correspond to the two different bounds, the lower bound and upper bound. So it all does make sense in the end. So now we just have to remember that the quadratic formula in this case says that if you have an equation that looks like ar squared plus br plus 1 equals 0, the quadratic formula tells us that the two solutions are negative b plus or minus the square root of b squared minus 4ac all over 2a. So running the quadratic formula here is going to give us what? Negative b, well, the coefficient in front of r is negative 2 times cosine theta plus sine theta. So the negative of that coefficient is 2 times cosine theta plus sine theta. Plus or minus the square root of b squared, again, here's negative b. So b squared is going to be 4, comes from 2 squared. And then I've got cosine theta plus sine theta squared. Minus 4ac. So minus 4a is 1. c is 1, so this is just minus 4. All of that over 2a. a is 1. So this is all over 2. And like I mentioned, these two different solutions here, these are the bounds. And we don't have to do this, but just because we may as well, I'll simplify this algebraically a little bit. And I'll do a lot in one go. Again, this is just algebra at this point, so don't worry about it too much. But 2 over 2 is 1, so I get a cosine theta plus sine theta. Plus or minus. The 4 here I can factor out of the square root and kill off the 2 in the bottom there. So that leaves me with just the square root of. And then the most complicated step that I'll do in my head is when I square this quantity, I'll get a cosine squared plus sine squared is 1 minus 1, so those cancel out, and then I'm left with the mixed term from this squared quantity, which is going to be 2 cosine theta sine theta. And it seems weird, but here we go. These are the two bounds for the R integral. It's something plus a positive number and then something minus a positive number. Geometrically, the bigger R values correspond to this chunk of the circle, and the smaller R values are the ones closer to the origin, so they correspond to this chunk of the circle. So that indicates that the upper bound here is probably given by blah 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 plus the square root of blah blah blah. And the lower bound is blah, 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 minus the square root of blah, 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 blah. So I'll awkwardly write these in here, and that will do it. The upper bound is going to be cosine plus sine plus the square root of 2 cosine sine. And the lower bound is going to be cosine plus sine minus the square root of blah, 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 blah. Not the prettiest iterated integral in the world, and I probably should have given myself a little more room for the R bounds, but it's correct.